I'll be doing a webinar on 70 volt basics, where to use low or high impedance systems, and the difference between them. What is a 70 volt high impedance system? It uses speakers designed for 100 volt, 70 volt, and 25 volt systems. Speakers have adjustable power taps on the speakers, usually in 3 dB steps. Amplifiers have a high voltage, high impedance output. Amplifiers deliver a constant voltage, so changing speaker loads do not affect speaker volumes connected on the same zone. Used mainly for distributed speaker systems comprising many speakers. Here's an example below of a F122, and the tap that you'd see, it's for 8 ohms, 16 ohms, or 100 volt, 70 volt, or 25 volt, and where you'd be using it on a amplifier, where you'd be connecting it. Here we have a typical low impedance system, and we're going to be adding an 8 ohm speaker and another 8 ohm speaker to an amplifier. Now, if you use Ohm's Law, we take 8 ohms divided by 2, being in parallel, gives us 4 ohms. So now that 8 ohm load is turned into a 4 ohm load. And a series connection, similar thing. You take an 8 ohm speaker, put another one in series. Again, using Ohm's Law, you've got 8 times 2 is 16 ohms. Where a high impedance speaker system, commonly known as a 70 volt system, you add one 70 volt speaker, another, and another, etc. The only limitation is wattage. 5 speakers at 1 watt each is a 5 watt load. Advantages when using high impedance systems. All speakers are connected in parallel. There's no series wiring required. No need to maintain a specific impedance load to the amplifier, only a minimum load. Failure of a speaker or an open speaker transformer will not cause the system to fail. A selection of power taps on each speaker allows for level adjustments in different areas to suit specific zone needs. Adding or removing speakers does not affect volume levels on existing speakers. Long speaker lines are possible with appropriate wire gauge, and use higher voltage amplifier outputs allows use of smaller wire gauge. Simple wall attenuators can be used to adjust the volumes in each zone, like our AT series TOA attenuators. A typical 70 volt system, you have a TOA amplifier there, and you have a background music source or a microphone, and you have one run going to the amplifier, and only one. And now out in the area in the zones, you have a 70 volt speaker system connected, and you have another section you want to add another speaker system that needs a volume control. You just tap off the original line. You don't have to home run them. That's the beauty, the simplicity of a 70 volt system. Some questions before designing the system. Where will the system be used? Will the system be used indoors or outdoors? Then we need to worry about selecting weather-resistant speakers. Is the indoor space highly reverberant or have a huge echo factor? Then a wide dispersion or narrow dispersion speaker has to be selected. What are the width, length, and height of the room needed for calculations? And for ceiling mount, is the ceiling an unducted return air, a plenum? Then we use a plenum rated speaker. So, number 2, what will the system be used for? Background music, foreground music, paging, signaling. What are the client's expectations for quality of sound? Do we need a lot of bass? Do we need subwoofers? When used for speech or paging, what level of intelligibility is expected? How loud will the system be? What's the ambient background noise level? Is the system used for foreground material? Number 4, how will the speakers be mounted? A ceiling, wall mount, flown, then we just select some brackets. Again, are we going to be using subwoofers? Number 5, what will the speaker spacing be? Depends on the standard speaker layout patterns of the square or hexagonal staggered pattern. After selecting the pattern, what performance or how even is the level between the speakers? Number 6, what amplifier power and wiring is recorded? Amplifier power will depend on the number and power setting of each speaker. Each speaker power tap setting will depend on distance of the speaker from the audience, the sound pressure level required, and the ambient noise levels. Wiring gauge size will depend on the length of the run and wattage delivered down the wire. Number 7, do we require signal processing? Some speaker systems will benefit from frequency correction to improve the sound quality or reduce feedback. The 9000 series, 901, or D2000 can achieve that. Muting capabilities may be required when distributing background sources and paging. Signal leveling and compression can be used to maintain a volume level and prevent excessive damaging signal levels. Again, the 9001 and the D2000 series can achieve this. Do we need multiple amplifier zones? Number 8. Does the audio system deliver different sound sources to different areas? Is multi-zone paging required? Select a multi-channel amplifier such as a 9000 M2 or the DA series. Number 9. What type of sound sources are required? Microphones for paging, like a TOA desktop mic, a PM660U. Telephone paging, they don't need a ZP001T module for the 9000 series. Music sources such as a CD, DVD, MP3, satellite, or music services. Pre-recorded digital messaging, we have modules or standalones for that. Tone modules for alert signaling, the S-series modules. The ability to mute background sources when paging. Mute, send, and receive capability. A control from the fire alarm panel for muting the audio system. And number 10, which type of system? High or low impedance? Low impedance. Generally, low impedance systems are used for performance, foreground systems such as concert halls, auditoriums, house of worship, arenas, etc. Low impedance systems require heavy gauge wire and require care and final speaker impedance. Wiring layout is more complicated because of trying to maintain a constant impedance. Constant and minimum impedance must be maintained by using series parallel wiring speakers. High impedance systems suitable for multi-zone paging and background music distribution. Wire gauge size is smaller, typically 18 or 16 gauge. Wiring layout is simplified. Easy volume control using wall attenuators, like our TOA AT series. Since all speakers are wired in parallel, no specific attention is required to maintain a constant impedance to the amplifier. Designing a system. Now we have asked the questions, where do we start? Sound pressure levels are expressed in decibels or dBs. Decibels are used to make very large numbers easy to manage. Typical dB levels are expressed from 0 dB, threshold of hearing, to 140 dB, permanent hearing damage. Some reference examples: 30 dB, soft whisper 5 feet, 50 dB, private business office, 70 dB, average male voice in conversation, and 90 dB, truck traffic, and 115, a rock concert. Average listener can just hear a 3 dB change in volume levels. Perception that the volume levels have doubled is 10 dB. Speaker sensitivity. Specification indicates how efficient a speaker is at producing sound. All manufacturers measure the speaker on axis at 1 meter distance, referred to as the reference distance, by applying 1 watt complex signal. This is referred to as a 1 watt per 1 meter specification under sensitivity. You'd see it like that on the display on a spec sheet. High sensitivity is desirable when we'll need less amplifier power per speaker. How much power to increase the volume levels? As we've seen, sensitivity rating tells us the volume levels and decibels of the speaker when we use 1 watt of power measured 1 meter from the speaker. Physics states that for every doubling of power we have a change of 3 dB. So if we increase the amplifier power from 1 watt to 2 watt, speaker that produced 90 dB at 1 meter will now produce 93 dB at 1 meter. Increase the power to 4 watts, and we add another 3 dB for a total of 96 dB at 1 meter. For example, 1 watt, 90 dB, 2 watt, 93 dB, 4 watt, 96 dB, 8 watt, 99 dB at 1 meter from the speaker. Loss of volume over distance. As we move farther away from the speaker, we hear that the sound level decreases. But by how much? Once again, physics tells us that the volume levels decrease for conventional speakers by 6 dB for every doubling of distance. Let's look at our speaker that's producing 90 dB using 1 watt of power at 1 meter. And of course, line arrays vary by 3 dB. If we listen to this speaker on axis at 2 meters distance, the sound pressure level will now be 90 dB minus 6 dB, which is 84 dB. If we move to 4 meters away, we've again doubled the distance. The volume will now be 78 dB. For example, 1 meter, 90 dB, 2 meters, 84, 4 meters, 78 dB, 8 meters, 72 dB. Why is this important? We can use these simple constants to make quick on-axis calculations of how loud the volume will be in decibels when the speaker is at a particular distance and the amplifier is providing a certain wattage. Simple example, calculate the SPL ear level for a 90 dB 1 watt per 1 meter speaker mounted in a ceiling 6 meters high. First, calculate the on-axis SPL at a distance of 4 meters, ear level, when the speaker is driven with 1 watt. SPL is sensitivity minus distance. So 90 dB minus 0 dB is 90 dB, 1 meter reference. 90 dB minus 6 dB is 84 dB, that's 2 meters. 84 dB minus 6 dB is 78 dB, 4 meters at ear level. The note is every time we doubled the distance, 6 dB was subtracted from the reference. The design calls for 84 dB at ear level. Now calculate the power required. 1 watt is 78 dB at ear level. Calculate above for 1 watt. 2 watt, 78 plus 3 dB is 81 dB. 4 watt, 81 plus 3 dB is 84 dB. And 8 watt, 84 dB plus 3 dB is 87. 16 watt, 87 plus 3 dB is 90 dB. So take 4 watts of power from the speaker to produce 84 dB at ear level. So we select the 5 watt tap on the speaker. So every time we doubled the power, we added 3 dB. What happens off axis? We saw the sound pressure levels decrease as we move away from the speaker. Volume levels decrease even more as we move off axis from the speaker. Speaker manufacturers define the coverage angles based on when the speaker levels off axis drop 6 dB from the on-axis response. Suppose the coverage specification for the speaker was 60 degrees horizontal at 2000 Hertz. This means the off-axis volume levels are down 6 dB, 30 degrees each side of the on-axis response in the horizontal plane. It's a diagram describing that there. Knowing the off-axis response of the speaker and the amount of even coverage required for the application will determine how many speakers and what the spacing will be between the speakers. The smaller the spacing, the more even the sound levels between the speakers. And there's a diagram there, and the graph below shows you the drop-off at the off-axis between speakers. That's what we have to count for. Angled paging horns. There's another example. 50-foot spacing, 20-foot ceiling. So knowing the dispersion angle, we aim the speaker so that the energy from the top of the speaker does not hit the ceiling. Since the off-axis dispersion is 30 degrees, aim the speaker down from horizontal 30 degrees. This will give you pretty even coverage and even sound along the distance. How much amplifier do I need? In our example, we found that a single speaker to produce 90 dB ear level required 16 watts. However, the application does not have a lot of ambient noise. As such, we'll use a lower tap setting that will produce 84 dB at ear level. We chose a 5 watt tap. If we know the total number of speakers per channel, we can calculate the total power the amplifier must produce. The design, after calculating spacing of speakers, requires 19 speakers. Since we're tapping the speakers at 5 watts each, the total wattage load from the speaker is 19 times 5, 95 watts. We must now add in some headroom to account for the speakers in the audio signal. As a rule of thumb, 20% is added. So 95 plus 20% comes out to 114 watts. So you select a TOA 120 watt 70 volt amplifier. Room setup. I need to quote an audio system. The room is 50 feet wide and 100 feet long. We have to consider the usage. Background music, probably get away with ceiling speakers. Foreground music, wall mount, high impact. PowerPoint, we're just going to have somebody speaking or some examples on a PowerPoint or computer. We have to consider that. DVD, theater style impact. I need something a little louder. Paging, strictly voice. Live band, we need a full frequency range. Here's we're comparing point source versus distributing. Here's a diagram of a point source where you have the speakers on one side of a room going across the entire room. An example of that would be, say, a educational facility or a church, house of worship. We'd be using a point source. Okay, point source pros and cons. If the ceiling's too high, on the pros, ceiling's too high, ceiling not suitable, trying to draw attention laterally. On the cons, it's too loud if you're too close, and you have minimal throw distance. And now here we see a diagram of distributed, where you'd say use this in a background music or paging. Speakers are in the ceiling, above you, evenly spaced, and designed so there's even coverage over the entire area. So the pros and cons of distributed. Pros, you got even coverage, non-obtrusive look, the size of the room is not really a factor, and ease of wiring. The cons, limited to size, and the sealing material will restrain certain installs. Now here's a commercial audio design worksheet available from your regional sales manager. Just a little aid to help you when you go to the site, and you can actually ask relevant questions that will help in the design. Again, the applications, what is it used for? Office, commercial, warehouse, industrial, outdoor, indoor, environmental considerations. Explosion proof, is it in a mine, at a gas station? Waterproof, is it going to be exposed to rain? Temperature, anything else that might be relevant to where the environments will have an impact on the equipment. Paging, what type of paging? Is it telephone? Is it through a microphone? How many microphones you need? The zones, number of zones, background music, yes or no? Do we have to mute the sources when we do paging? Only in certain areas? All the areas the music has to be muted? Where is the music going to be? A typical example would be a service dealership where you have a showroom and a shop. And typically the installs have been they want music in the office area and the showroom, but not in the shops. But you'd have your paging in the whole area and all the zones. So that's a consideration. Volume controls. Is it going to be central or local in each room or each area? The audio sources, do you have, how many audio sources? Maybe you have a Muzak system or just a microphone. Do you have a telephone, CD? Speaker requirements, is it surface mount, is it flush mount, square, does it need back boxes or just horns? Speaker quality, if you have ceiling speakers, if it's just for background music and paging, maybe you can get away with the less expensive speakers, but if you want better quality, maybe look at the F-122. And location of the equipment of the building, is it shelf mounted, is it in a rack? Do we have CAD drawings of the site? All this would help. And of course, the summary at the end, number of zones, length, time, width, and height of the rooms, the ambient noise level, which at the bottom of the sheet you can see a reference for noise levels we can put in there. We get a rough estimate of what it is and what they're trying to achieve as a paging level above that noise level. Is it flush mount? Do we use background music there? Speaker types? Again, little ticks on there. And when you show up to a site with a sheet like this and you're asking relevant and important questions, it may set you aside from, say, the fellows that didn't come prepared. And again, if you need our fellows at tech support to help you design a system, the more the information you can fill out on the sheet, the easier it's going to be, and the quicker the turnaround time will be on the specification for the equipment and where to mount it. Here's an easy way to calculate SPL and speaker spacing. TOA is a program for doing all the basic calculations for estimating sound pressure levels, speaker placement, total wattage required by the amplifiers, and the evenness of the sound between the speakers. It's called the Speaker Placement Viewer. It's available on the link you see there. Next slide here, I'll have a look at that. Yeah, now here's a screenshot of what you'd actually see on this Speaker Placement Viewer. You start with your length, width, and height of the room you're designing the audio system for. You pick your speaker, your TOA speaker, and you enter the relevant information, and it'll come up with a diagram as you see in the slide. Now, this can be printed, and again, it's something you can take with you to the client once you've done your speccing. This is what to expect. This is what the speaker should go. And it does help if you have this on your side. And again, it's available free from the link on the previous slide. What type of wire for the speakers? For high impedance speaker systems, we've seen typically smaller gauge wiring is used. For speakers, unshielded, 2-conductor, non-twisted, stranded wire is used. Gauge size will depend on the total wattage to the speaker zone and length of the wire. For example, if we have an amplifier, we must deliver 100 watts to all the speakers in one zone. The total distance of the last speaker is 720 feet. The wire gauge required is 16 gauge, as we see in the data table there. Here's some of TOA's high and low impedance amplifiers. You see the BA and BG series there, the A series. The DA series, high power amplifiers. The wall amplifiers, the 9000. What's not on here is the D2000 series. The wall amplifiers, like used in the schools, are still available. Just keep that in mind. And of course the speakers. We've got on this slide showing a lot of what's current here. The PE series hanging ones, the line arrays, used in a lot of the arenas. Have used them in some churches, house of worships. Very popular for that now. Something that's not on the slide is the ceiling mount speakers are now also available in a square grill. So for some of those retro installs that we need to get fixed up and leave the same look or fill the same spot.